welcome back to the deep dive. I want to start today by asking you to just visualize a scenario.
Okay.
You're in a foreign country, you don't speak a word of the language, and you need to ask for a drink of water. What do you do?
Well, that's easy. I mime it. I pretend to hold a glass, tip my head back.
The universal sign for I'm thirsty.
Right.
Exactly. And because we can do that, because we can pantomime our basic needs, we have this really deeply ingrained assumption that sign language is just a more elaborate version of that.
That it's basically just pictures in the air.
Right, which leads to that universal myth, the idea that if you learn sign language, you've got this passport to communicate with any deaf person on Earth.
Yeah.
But today, we are tearing that entire assumption down. We're digging into a paper by David Carina and Heather Knapp called Psycholinguistic and Neurolinguistic Perspectives on Sign Languages.
And this really isn't just about how deaf people communicate. It's about figuring out what language actually is to the human brain.
That's the core of it, isn't it? Is language fundamentally a sound-based system that we've just, adapted for other things?
Or is it something more abstract, a biological machine that honestly doesn't care if the input comes from the ear or the eye?
Well, the evidence we're going to look at today suggests the latter, and it gets pretty wild.
It does.
We're going to talk about slips of the hand. We'll see what happens to a signer's brain during a stroke, and we'll discuss why a signer might actually recognize a word faster than you or I could.
It really challenges a lot of what we think we know about cognitive processing.
So let's start with the basics. If sign language isn't just pantomime, then what is it? Because to me, if I see someone sign tree, and it kind of looks like a tree, that feels like a picture.
And some signs are iconic, sure, but the paper makes it really clear. Sign languages like American Sign Language or ASL, they're autonomous linguistic systems.
Meaning ASL isn't just English on the hands.
No, not even close. It has its own grammar, its own syntax, and it evolves naturally, inside communities.
So that's why you have, like, Langue des Signes du Québec.
LSQ, yeah, or Taiwan Ziran Shuyu. An ASL signer can't understand a user of LSQ, even though they're basically neighbors.
That blows my mind. You'd think the picture for something like a house or a tree would be the same everywhere.
But they're not pictures, they're symbols. And they're constructed from very specific building blocks. In spoken language, we use phonemes, right? Sounds.
Right.
In sign language, we use what are called parameters.
The paper mentioned William Stokoe was the one who first figured this out. He argued that signs have phonology, which, that feels like a contradiction. Phonology is about sound.
In the strict sense, yes. But in linguistics, phonology is really just the study of the smallest units of language, the building blocks. And Stokoe identified that every single sign is built from 4 main parameters.
Handshape, location, movement, and orientation.
Exactly. So it's not just random waving.
It's more like a combination lock.
That's a great way to put it. To produce a sign correctly, you need the specific hand shape of fist versus an open palm. You need the location, is it on your chin or your chest? The movement, is it up, down, circular?
And the orientation, so palm in or palm out.
Right. And if you change just one of those...
You change the entire meaning.
It's the difference between cat and bat. If you keep the location and the movement the same, but just swap the hand shape, you've made a completely new word. Or, just nonsense.
The brain has to track all 4 of those parallel tracks instantly to decode the meaning.
And that right there leads us to one of the most surprising findings in Carina and Knapp's work.
Which is the speed of recognition.
It's the speed of recognition, yeah.
This was the gating study. I have to admit, I read this section twice because the numbers just seemed backward to me.
The Emery and Carina study, it's a classic setup. They take a word, either spoken or signed, and they reveal it in these tiny little increments, like 33 milliseconds at a time.
And they want to know how soon the brain goes, aha, I know that word.
Exactly. For spoken English, the stat was pretty high.
83%.
Yeah.
You need to hear almost the entire word before you lock it in.
Right. Because speech is linear. It unfolds over time. If I start saying elef, you have to wait for that ant to be sure I'm not about to say elevator.
But for signers, it was totally different.
They recognized the sign after seeing only 35% of it.
That is absurdly fast. That's barely a third of the signal. How is that possible?
It's the architecture of the signal itself. Speech is sequential. Sign is simultaneous. When I make a sign, you see the hand shape, the location, and the movement all at once. It's like a parallel data dump into your brain.
So you're getting all the clues instantly.
Instantly. Plus, there's this thing called co-articulation. Signers can pick up on really subtle physical cues. So if my hand starts moving toward my forehead, your brain is already ruling out every single sign that happens at the chest.
You're narrowing the search field much faster than a listener can.
Much faster. It's incredibly efficient. But, as efficient as it is, the system can still crash.
Right. We've all had that moment where a word just vanishes. It's on the tip of my tongue.
And the sign language equivalent is the tip of the finger.
I love that that's a real clinical term.
It is. And when you study it, it tells you so much about how the brain stores this information. When a signer has a TOF moment, they don't just go blank.
They remember parts of it?
Yes, usually specific parts. They tend to remember the location and the orientation. They know where the sign is supposed to happen, and they know which way their hand is supposed to face.
But they can't retrieve the movement.
The movement, or sometimes the hand shape, that's what gets lost.
That's fascinating. It's like the brain has these parameters filed in different folders. You've opened the location folder, but the movement file is like corrupted.
Precisely. It confirms that signs aren't stored as these holistic pictures. They're stored as assembled components, and sometimes the assembly line just jams.
Which brings us to slips of the hand, the signing world's version of a typo.
And these are great because they mirror spoken errors so perfectly. In speech, we might accidentally swap a sound, saying piggle instead of pickle.
Right.
In sign, the research shows that the vast majority of these errors, these slips, happen with the hand shape.
Why is the hand shape the weak link?
It's probably the most complex parameter. I mean, think about it. There are so many more possible hand shapes than there are, say, locations on the body. It's probably the most consonant-like part of the sign.
So just like we stumble over complex consonant clusters, signers can trip up on these complex hand configurations.
Exactly.
Okay, the paper also detailed an experiment about priming and interference. The Stroop-like task?
Oh, the interference effect. Yeah, this was very clever.
It sounded terrible for the participants.
Well, I'm sure it was. So they wanted to see if watching one sign would interfere with your ability to produce a different one. So they'd ask a signer to name a picture, let's say a picture of a chair.
Okay.
But while they're trying to sign chair, they're watching a video of someone else signing apple.
Which sounds distracting for anyone.
But here's the kicker. It was only significantly distracting if the two signs shared a parameter.
So if apple and chair both use the same location or the same kind of movement?
The signer slowed way down. Their brain was getting cross signals.
Wow.
It proves that your mental lexicon, your internal dictionary, is organized by these structural features. Signs that look alike actually live next door to each other in your brain.
That brings me to the idea of the inner voice, or I guess in this case, the inner hand, because I know how I rehearse a phone number in my head. I say it over and over. But if you've never heard a number, how do you rehearse it?
You still use the phonological loop. It's adapted for vision. Signers have an internal inner signing loop.
And they prove this by making people move their hands while trying to remember things.
It's a technique called articulatory spickpression. If I ask you to memorize a list of words, but I make you say the out loud the whole time, you can't do it.
Because my loop is busy.
Your loop is busy. So they did the same with signers. They gave them a list of signs to remember, but then asked them to just repetitively open and close their hands while they watched.
Occupying their manual articulator.
Right. And what happened?
Their memory scores dropped.
Plummeted. It proves that working memory requires active rehearsal. And for signers, that rehearsal is physical, even if it's just happening in their brain. They're simulating the movement.
There was also the word length effect. In English, a long word like university is harder to remember than a short word like cat because it takes longer to say.
And in sign, long means physical distance. Signs that require a large movement through space, say moving from your waist up to your shoulder, take up more capacity in working memory.
That is such a concrete validation that memory is time-based. It's not about how much information is in the word, it's about the playback time.
Exactly. The inner loop runs in real time.
Okay, so we've established the software. Let's talk about the hardware, the brain itself. This is where I think anyone's intuition just completely breaks down.
You mean the whole left brain versus right brain thing?
Right. If you ask me, where does sign language live in the brain? I'd say the right hemisphere. 100%. It's visual, it's spatial, it's 3D. That's what the right hemisphere does.
And that is a very logical and a very wrong assumption.
So break it down for me.
The paper is definitive on this. Sign language is processed primarily in the left hemisphere.
Just like spoken language.
Just like spoken language, the brain's language tag completely overrides the visual tag.
And we know this from studying aphasia language loss from brain damage.
Right. The case of patient GD is the smoking gun here.
Walk us through her case.
So GD was a lifelong signer who had a stroke in her left frontal lobe, what we call Broca's area in hearing people.
And Broca's area handles speech production, grammar.
Exactly. When it's damaged in a speaker, they become non-fluent. They speak in these broken, halting, telegram-style sentences.
And
The exact same profile. She could understand signs perfectly. But her production just fell apart. She was reduced to single signs, and crucially, she became agrammatic. She stopped using all the complex grammatical movements in ASL.
But was it a motor issue? I mean, maybe she just couldn't move her hands smoothly anymore.
That's the first question you have to ask, but no. She could use her hands perfectly fine for non-linguistic tasks like waving goodbye or grasping an object. She just couldn't use them for language.
That distinction is incredible. The brain literally separates moving my hand from signing a word.
It really is.
Yeah.
And then you see the substitution errors or paraphasias, just like a speaker with aphasia might say dog when they mean cat.
Signers make semantic errors, signing bed instead of chair.
Yes, but the form-based errors are the ones that really drive home that parts theory we talked about. Patient WL is the example. He tried to sign screwdriver.
Right.
He got the location right. He got the movement right. But he used the wrong hand shape. He used an A hand shape, a fist, instead of the required H hand shape.
So the handshape file was the only one that didn't load properly.
Exactly. But my favorite error, if you can have a favorite brain injury symptom, has to be the blend.
The tree in green example.
This is such a vivid look inside the brain. So patient WL was asked to sign tree, but just seconds before, he'd been primed with the color green.
Okay, so tree and green.
Now, the sign for tree involves the forearm held upright with the hand waving. The sign for green involves a twisting motion of the wrist. Two totally different signs.
Right.
But WL signed tree while twisting his wrist.
He mashed them together.
He physically blended the phonology of the two separate concepts. It's a visual slip of the tongue. It shows that both of those concepts were active in his brain, and the mechanism that's supposed to inhibit the wrong one, it failed.
That is wild. It's like watching two video tracks get overlaid on top of each other.
It is, and we can get even more granular with this with cortical stimulation mapping.
This is the awake brain surgery.
Yes. With patient ST, doctors needed to map his language centers, so they stimulate tiny spots on his brain with an electrode while he's signing.
And when they zapped the left hemisphere,
When they stimulated Broca's area, his hands started mumbling.
mumbling hands.
That's what they call it. Laxed articulation. His hand shapes just sort of collapsed into loose fists. His movements became small and repetitive. It was a motor execution failure.
But then they moved the electrode to a different spot, the supramarginal gyrus, the SMG.
And the error changed completely. It became a selection error.
A selection error.
He tried to sign peanut, which involves flicking the thumb off the teeth. But when the SMG was stimulated, he formed the wrong hand shape. He realized it was wrong. He tried to fix it, but then he messed up the movement.
He was debugging his own sign in real time.
He was. It suggests the SMG is responsible for assembling the phonological parts, selecting the right Lego blocks before sending them to Broca's area to be executed.
So, if the left hemisphere is doing all of this heavy lifting, grammar, selection, production, does the right hemisphere do anything? I mean, we agreed earlier, sign is spatial.
It is, and the right hemisphere is involved, but in a really nuanced way. The research distinguishes between topographic space and grammatical space.
Okay, that sounds technical. What's the difference?
Topographic space is basically a map. If I tell you the cable is on my left and the door is on my right, I'm describing the physical layout of a room.
And that recruits the right hemisphere.
Yes, because it's a special mapping task. But if I say, John is nice, I like him, and I set up John in a specific spot in space to my left, and then point back to that spot later to say him.
That's grammar. That's syntax.
That is grammatical space, and that stays firmly in the left hemisphere. The brain is smart enough to distinguish between a point in space that's a map and a point in space that's a pronoun.
That's a subtle but massive distinction.
It is, and there's one final piece about the right hemisphere that I think is fascinating, the right angular gyrus.
This was the native signer signature.
Right. Brain scans show this area lights up significantly during signing, but only for native signers, people who learned ASL from birth.
So if I started learning ASL today, even if I became fluent, my brain wouldn't do that.
Likely not. It seems to be a neural footprint of learning a visual language during that critical childhood development window. It shows that while the brain is adaptable, early experience really does wire it in specific ways.
So we've covered a lot. We've gone from the basic building blocks to brain surgery. When you look at Karina and Knapp's work as a whole, what's the headline for you?
For me, it completely reframes the definition of language. We tend to think of language and speech as being, synonymous.
Yeah.
But this research proves that language with a capital L is a central, abstract operating system in the brain.
An OS that doesn't care about the peripherals you plug into it.
Exactly. You plug in a microphone and speakers, it runs the speech app. You plug in a camera and mechanical arms, it runs the sign app. But the core code, the syntax, the lexicon, the processing areas is remarkably preserved.
It really challenges the idea that language is something we invented. It feels more like something we are.
It suggests the capacity for this complex, rule-based communication is a biological instinct. It's just waiting there, ready to organize whatever input it gets.
It makes you wonder if we ever met an alien species that communicated by, I don't know, flashing colors on their skin.
Would their brains have a Broca's area?
Yeah.
If their language has grammar, I'd bet on it.
That is a fascinating thought to end on. Language isn't about the ear or the eye. It's about the mind.
It really is.
Thank you so much for walking us through this, and thank you to everyone listening. Hopefully the next time you see someone signing, you'll see not just gestures, but a complex linguistic engine firing on all cylinders.
Thanks for listening.
We'll see you next time on The Deep Dive.